Okay, this video is Carbohydrate Nutritional Biochemistry Part 1. We're going to talk about the biochemistry related to advanced glycation end products. Here's just a list of the amount of advanced glycation end products in foods. There's two sets of them that we mostly think about. The ones produced in the body, especially due to hyperglycemia, high blood glucose levels, and there's also some issues with fructose. Then there are the advanced glycation end products from food. So they're especially common in fried foods and especially common in high protein, high fat foods. So look at bacon, like 12,000 per serving, off the charts. So in general, all the animal foods, especially if they're fried, have much higher levels of advanced glycation end products related to cooking. With the browning of a food, when you cook it, that's partly what these glycation end products are. And they actually taste good, but they're not good for one's health. And some of them are absorbed. Olive oil is bad. All these fatty things, mayonnaise, avocados are bad. When you start getting down into fruits and vegetables, they're very low, and you want them to be low. So anyways, we'll go into what this all means here now with the next couple of pictures. Okay, these are the general categories of carbohydrates. Monosaccharides have a single sugar unit, and that's just like your glucose or your fructose or galactose. Disaccharide is two sugar units. So the classic one, white table sugar, cane sugar, beet sugar, it's all sucrose, and that is a glucose molecule and a fructose molecule bound together. So lactose, the milk sugar, is also a disaccharide, a glucose and a galactose. Maltose is just two glucose stuck together. You'll sometimes hear that word used, and there's sometimes versions of that added to foods. Oligo just means, oligo means a few, oligosaccharides, so 3 to 10 sugar units. Dextrins are primarily breakdown products of starch from digestion. You'll hear that, and they're different lengths, and they can be limited in certain ways. You'll see those sometimes in food, limited dextrins, maltodextrins. That's what that's all about. And then polysaccharides are many sugars all joined together, and there can be hundreds and hundreds of them all joined together. Starch is the classic one that we eat. Amylose is a straight chain, slower to digest because the enzymes have to work on the ends. Amylopectin is branched, and when it's branched, the enzymes can get more rapid access to the ends, so that'll be digested faster. Fiber has a different type of connection between the sugars. Even though it's glucose, they're connected in a different way that we don't have enzymes to digest, human enzymes. But the bacteria in our colon can process the fiber. Glycogen is how we store glucose in our body, and it's highly branched, and all the branches means that it can be broken down very quickly when necessary for energy in a fight or flight moment. Okay, here's we're going to get into a little bit of biochemistry. I'm going to keep it to a minimum, just what you need to know to make sense of stuff. There's certain things that are worth knowing. So the smallest sugars are 3 carbon units. When they've got a ketone on here. So this is a carbonyl carbon. A carbonyl carbon is when there's a double bond to the oxygen. When there's a carbon on both sides of it, then it's called a ketone. All right, when the double bond to the oxygen is at the end of the molecule, and there's just a hydrogen also coming off that carbon. All carbons form four bonds. So this one has 1 to this carbon, 1 to this hydrogen, and 2 to this oxygen. That will be called an aldehyde. These are super common, important molecules to know about in carbohydrate metabolism. Dihydroxyacetone is a key player with the ketone. Fructose, by the way, also is a ketone. I think of fructose as being fructone. If you care about it, later on we'll get into future lectures about some of the subtleties of carbohydrate metabolism, and that will end up being useful to know. Fructone. And I think of glucose as being glucose. We're going to talk about that in a moment, but it's an aldehyde. Aldehydes are actually more reactive than ketones. And then one looks at the hydroxyl groups here. The hydroxyl group of the last chiral carbon. A chiral carbon means that it has 4 different things that it's attached to. It's also called an asymmetric carbon. So in this molecule, there aren't any chiral carbons. But in this glyceraldehyde, is an important molecule right in the center of glycolysis, the pathway for anaerobic metabolism of glucose. We have a chiral carbon because it's got a different thing on all 4 of its attachments. So for the chiral carbon, that adds chirality to it. And this is called a Fischer projection when it's written in an open linear form. And the key thing to know is on the last chiral carbon, the one farthest away from the carbonyl group, that's also called the anomer carbon, the one farthest away, if you draw the hydroxyl group to the right side, that's going to be dextrose. D for dextrose, D So this is D-glyceraldehyde. Because it's an aldehyde, it's also called an aldose type sugar. Something that has a ketone in it that's a sugar is called a ketose type sugar. They have the same molecular formula, by the way. So these are called isomers, meaning there's the same molecular formula if you drew what they contain, but they're connected in different ways. Okay, now this would be L-glyceraldehyde, meaning that at the last chiral carbon, the hydroxyl group's on the left side. But in nature and in the human body, almost all of your sugars are going to be of the D form, the dextrose form, which means the right-sided when drawn in the linear configuration. The way I remember this is DOAG, like a dog, but D-O-A-G. And I just think of that as dexter, right-sided, oxygen of hydroxyl group. And I remember that it's an aldehyde, my glyceraldehyde. And again, you don't need to know this right now, but if you are curious about carbohydrate metabolism, these little tricks become helpful. And this is different than an amino acid. I think of amino acid like the name for an Irish girl. She's a lassie. L-A-S-S. L for left chirality, amino acid. And S for sinister means left also. So anyways, the point of this slide was there is a chiral carbon which has 4 separate different attachments, and the last one is the designation of D, and most sugars in the human body are D. So for what it's worth, we'll later come back to that, and I promise you there's going to be something really useful come out of this talk. Okay, now a little more nomenclature, because you have to get some of this nomenclature at the beginning to make sense of stuff later. So here is glucose. It's a D form because this is on the right side. So D is dexter, that's right side. It's in the open chain form. It's opened up. In real life, in solution, only 1% or less than 1% of the glucose is going to be in open chain form. It's called the Fischer projection. Fischer was actually the mentor of Otto Warburg in biochemistry. And the Fischer projection, I remember if you go fishing, you cast a line, it's a straight line. So a straight line linear way to draw a sugar is called a Fischer projection. And that's in comparison to these ring forms, which are called Haworth projections. I remember the actress Rita Hayworth, big breasts and a circle, a breast is like a circle. So that's Haworth projection on how to draw it. In real life, most glucose is going to be in these ring forms, okay, either the alpha ring or the beta ring. The way I remember the alpha ring is alpha has a shorter height, and so that's the hydroxyl group is lower down, okay? Beta is a taller thing than an alpha, so I remember it's taller and the hydroxyl group is going to be above. Again, these are relatively minor details, but for carbohydrate biochemistry, it's worth knowing those few things. Here's the Fischer projection now cyclized, and you can see when this carbon number 5, the farthest away chiral carbon, reacts with the carbonyl carbon, it was a carbonyl carbon, then it forms a ring form. Okay, and what happens in real life is it'll be in one ring form, it'll open up, it'll form the other ring form, and it'll go back and forth. And the relevance is that when it's in the open form, it's much more highly reactive because of this aldehyde at the end. The little asterisk means anomer carbon, which is the carbon with the carbonyl group on it. And that's a relatively highly reactive part of this molecule when it's in the open form. And here we're showing it cycling between this ring form, the alpha ring form, to the linear form, to the beta form. Okay, well, I would go all the way over here, linear, and then to the beta form. And during that moment when it opens up, that linear form can react with other things, including proteins in the blood, the albumin. It can react with the hemoglobin. That's hemoglobin A1C for monitoring diabetics over the last 3 months. It can also react with collagen and form stiffening of collagen. And that's kind of what this talk is getting at. We're talking about how to slow aging. Okay, so the consequences of this ring opening up is when it's open, it can react with adjacent proteins. So the carbonyl group here, again, carbonyl means double bond to oxygen, that's the anomer carbon. This will react with the nitrogen. It can react with the trailing nitrogen at the end of a molecule, like of a hemoglobin, like just a valine amino acid residue, or more commonly with other proteins, they'll have a lysine side group chain of an amino acid, and it'll react with that. And it forms an irreversible connection. You know, the steps, if you look in a chemistry book, it'll be shift base and then Amadori rearrangement. You don't need to know that, but just so you've heard of it in case you wonder. All right, so this carbon that was originally our carbonyl carbon is now going to form a covalent bond with the nitrogen, and that becomes irreversible. Those are tightly stuck together. And so this is called an advanced glycation end product. It's called glycation because it's had a sugar added. To add a sugar to something is to glycate it. It's called an end product for our purposes because it's irreversible. That's it. Now it is going to be that until it's destroyed or removed from the body. Okay, now here's an article about advanced glycation end products and diabetic complications. And so kind of what is the whole point of this talk? You saw that the animal foods and the fried foods give you tons of dietary advanced glycation end products. Plus, these same high-fat foods elevate your insulin resistance, which then blocks the uptake of your cells, your skeletal muscle and other cells with glucose type 4 transporters, so that the glucose can't get into those skeletal muscle cells, some of your brain neurons, and a few other locations. And that drives up your blood glucose. When your blood glucose is high, the extra blood glucose in the blood, some of it will be in open form and it'll start reacting with other things, forming these AGEs. So this is another reason why it's obvious, if you look at the biochemistry, you want to minimize dietary fat. There's so many people on the internet that are full of BS, ignorant or liars, that are telling people to eat high-fat diets, and there are very good reasons why you don't want to do that. Okay, so here's a paper about advanced glycation end products and diabetic complications. This is from the Korean Journal of Physiology and Pharmacology, February 2014. Glucose forms covalent adducts, AGEs, known as glycation AGEs. And then these are associated with the complications of diabetes, like retinopathy, going blind, nephropathy, kidney failure, a disaster, neuropathy, painful neuropathies in the legs and whatnot. It also causes brain damage. Well, we're not going to focus on that for this lecture, but these same things cause brain damage. Cardiomyopathy damages the heart. Most common reason diabetics die is myocardial infarction. Also causes arthritis, painful joints, osteoporosis, loss of bone from the spine. It stiffens the collagen. These old people, they get all stiff because this is a major contributor to it. AGEs interact with plasma membrane localized receptors. So the receptor for an AGE is called a RAGE receptor. So here's it is, RAGE, receptor for advanced glycation end product. They will then, once they've activated the receptor for advanced glycation end products, the RAGE receptors, it will then activate additional inflammatory pathways, something called nuclear factor kappa B, changes gene transcription, produces all these inflammatory secondary messengers, molecules, does everything bad, makes your blood vessels more prothrombotic, prone to clotting. Oxidative stress can damage DNA and other tissues. It causes inflammation. And then here's an interesting statement. Look at this. Diabetes and its complications are rapidly becoming the world's most significant cause of morbidity and mortality. I can tell you, more than 90% of the brains I look at, demented people, they got diabetes. Most diabetics over 50 years of age that I talk to are cognitively impaired, really mentally slow. It's a disaster. This is what's killing people and making them sick and ruining their lives. And it's totally preventable. It's just, ignorance that causes us almost all these cases of type 2 diabetes. And it's easy to prevent. So that's why this is worth knowing. The cells expressing high levels of glucose transporter type 1, such as vascular endothelial cells, are unable to regulate intracellular glucose concentrations and are thus most susceptible to hyperglycemia-induced damage. So, okay, what am I talking about there? Your skeletal muscle cells and your muscles, they'll only take up glucose after eating a meal when they're sensitive to insulin. The glucose type 4 transporters are in a vesicle and they then merge up to the plasma membrane of the skeletal muscle upon the signal of insulin to say that it's time to do so. Okay, so those cells only take up insulin when they're insulin sensitive. They can also get it from exercise, but the point I'm saying is they're not going to get overwhelmed by glucose initially because of their glucose uptake is regulated. But the endothelial cells lining your arteries, they are not regulated. They're always active. And whatever your blood glucose level is, they're going to take up more glucose in proportion to that. So if you're running constant around the clock high blood glucose levels, you're going to put too much glucose into those cells and it damages them. Just like elevated fat in your skeletal muscle cells causes reversal of electron transport, Excessive amounts of glucose, uncontrolled, going into your endothelial cells and into your peripheral nerve cells and in some of your kidney cells is going to cause overwhelming of the electron transport chain with reversal of electron transport, reversal of Krebs cycle, reversal of glycolysis, a metabolic disaster. So what starts this whole process? Dietary fat, okay? And dietary AGEs, okay? You don't want this stuff. Mesangial cells overexpressing GLUT1, plus your blood-brain barrier has GLUT1, so you're flooding your brain with this crap. You don't want that. So here it is. Protein glycation reactions leading to advanced glycation end products are thought to be the major causes of different diabetic complications. Yeah, these things are a metabolic disaster. Okay, continuing. This is all from that same paper, Korean Journal of Physiology and Pharmacology, showing that when you have persistently elevated blood glucose, you get glycation of your proteins, and then look at all the downstream negative effects this has. You get increased platelet activation and aggregation. Well, increased platelet activation can hide metastatic tumor, increase your risk of cancer metastases, all right? It binds with your collagen, and it'll cause aging of your skin, more wrinkles. It increases atherosclerosis and causes fibrosis. That means scar tissue, scarred collagen. That means stiffening of your bodily tissues. And we talked about how damage to the collagen also is associated with back pain. Fibrinogen makes the blood more prone to clotting. Bad. Impairs endothelial function, the cells lining the arteries, leading to more microvascular disease. Blindness, brain damage, loss of neurons. Down in the foot, loss of toes, amputations due to gangrene of the foot. By the way, I see this every day. This is common stuff. Okay, autoimmune disease. If you damage a protein, you can confuse the immune system and make it think that it's a foreign protein and cause the immune system to attack it. Okay, advanced glycation end products are due to the endogenous ones. Endogenous means from the body, are produced by excessive blood glucose level. Also, can be excess fructose ingestion can do that too. That's a special circumstance. We'll talk about that in some other lecture. AGEs from excessive meat and fried foods. Yeah, you don't want to be eating those things. It's especially the high-fat, high-protein foods, as in meat and some of the processed foods. AGEs are very low in plant foods. Other than nuts, if you fry a nut, then they're pretty high. RBCs, they live about 120 days, red blood cells, which is about 3 months. So when the hemoglobin is glycated, the last valine residue on hemoglobin, that's irreversible. And so hemoglobin A1C, which is a measure of hemoglobin glycation, is an indicator of how good blood glucose control has been for the past 3 months. So let's say normally you want it less than 5.6. That's a normal hemoglobin A1C. 5.6 to 6.5 is pre-diabetes. When it goes above 6.5, that's diabetes. And some people, depending on what you say, over 7.5 or so, it's poorly controlled diabetes. The higher it is, the more complications are likely to occur. Okay, so let's just take one last look at these foods here. Look at this. Fried bacon, 12,000 units of AGE per serving. Hot dog is in that ballpark. Fast food cheeseburger from these fast food places. I didn't include the brand here, but it's one of the famous ones everybody that eats fast food goes to. 8,000. Grilled beef in the ballpark. Cheese up in that ballpark. Salmon broiled. Walnuts roasted. So if you roast walnuts or almonds or peanut butter, they're pretty high up there. It's another reason why I don't eat that stuff. Because a lot of people ask me about nuts. Oh, nuts are healthy. I don't think nuts are that healthy. Now, don't get me wrong. These are roasted, so a raw nut would be better than this, significantly better than this. But the excessive amount of fat in nuts, and I think nuts are quite overrated, by the way. And I think they had some funding of the Seventh-day Adventists. So you're going to hear, oh, nuts recommended. They're not as good as people think they are. A lot of the research on nuts has been industry funded. There's more to nuts. We won't talk about it in this lecture, but my opinion after studying them a bit is they're overrated. I might have a teaspoonful or a tablespoon on a holiday, if I'm but I would not eat them on a routine basis. You don't want all that fat, would be my opinion. Okay, olive oil's got a lot. Same with mayonnaise and avocados. High-fat foods have a lot of AGEs. They just tend to. If you toast a bagel, you're going to get them up there. A baked potato's got a lot more than just a white boiled potato. Oatmeal is, got about 20, still pretty low. I think oatmeal is a good food. A little higher in fat than the other starches, but still pretty good food. Apples about 13, quite low. White rice, banana, carrots, all real low, like around 10. So anyways, that's the point. Avoiding high fat foods, high protein foods, fried, baked foods, all the animal foods. You dramatically lower your AGEs, advanced glycation end products. You dramatically lower your risk of type 2 diabetes. You will improve blood glucose control in a type 1 diabetic, so you'll be likely to need less insulin dosages. And in the long run, this helps keeps all your arteries open and keeps your collagen from being stiffened and scarred and fibrosed. So you'll be more flexible, you'll be more young looking, you'll have less wrinkles. It's all good avoiding this stuff.